us journey together through the story of the moon and the human mind. A tale written across 4.5 billion years, told in silver light and neural pathways. Close your eyes, breathe deeply, and let the story unfold. In the beginning, there was chaos. Our Earth, young and molten, spun alone through the darkness of space. And then, in a cosmic dance of destruction and creation, a Mars-sized body called Theia collided with our planet. The impact was so tremendous that it liquefied both worlds, sending massive clouds of vaporized rock spiraling into orbit. This debris, still glowing with the heat of creation, began to coalesce. Within just 100 years, perhaps less, the moon was born from this ring of destruction, pulling itself together through gravity's patient embrace. At first, the newborn moon hung impossibly close to Earth, appearing perhaps 15 to 20 times larger in the sky than it does today. It loomed overhead, filling the horizon, close enough that you could have seen vast detail across its surface with the naked eye. The Earth spun wildly in those early days, and a single day lasted only about 5 hours. The moon's gravitational pull was immense at this distance, creating tides of unimaginable power. These weren't merely water tides but earth tides, where the entire surface of our planet rose and fell by hundreds of feet, the rock itself flowing like a sluggish ocean under the moon's influence. But nothing in the cosmos remained still. The moon began its slow retreat, pulling away from Earth at a rate of about 1.5 inches per year, the same rate at which your fingernails grow. This retreat continues to this very night. As you sleep, the moon drifts ever so slightly farther away, a gradual goodbye played out over eons. In another 50 billion years, if our solar system were to survive that long, the moon would appear as little more than a bright star in Earth's sky. Yet this retreat has been a gift to life. As the moon pulled away, it stabilized Earth's axial tilt to the gentle 23.5-degree angle we know today. Without the moon's gravitational influence, Earth's axis would wobble chaotically, swinging perhaps as much as 85 degrees over millions of years. Our seasons would become catastrophic, unpredictable. The poles would point toward the sun, then away, creating temperature swings that would make complex life nearly impossible. The moon became Earth's gyroscope, holding our planet steady in space, creating the stable climate that allowed life to flourish and evolve. And as life evolved, so too did its relationship with lunar light. The moon doesn't generate its own illumination but reflects the sun's light with remarkable consistency. The lunar surface has an average reflectivity, or albedo, of only about 12%. This means the moon is actually quite dark, roughly as reflective as worn asphalt. Yet because the sun is so brilliant and the moon so large in our sky, this reflected light has been bright enough to shape the evolution of life on Earth. Consider the nocturnal creatures that emerged in Earth's evolutionary story. For hundreds of millions of years, animals have navigated by moonlight. The dung beetles of Africa orient themselves by the glow of the Milky Way and the moon, rolling their precious spheres in perfectly straight lines across the desert floor. Sea turtle hatchlings emerge from their sandy nests under cover of darkness, instinctively crawling toward the brightest horizon, which naturally would be moonlight reflecting off the ocean. Countless species of moths, owls, and night-blooming flowers evolved their strategies around the moon's reliable monthly cycle of light and shadow. And then humans arrived, with our oversized brains and our hunger for meaning. We looked up at the moon and saw not just a light in the darkness but a mystery to be understood. The earliest humans watched the moon change its face each night, waxing and waning through its 29.5-day cycle. This lunar month became one of humanity's first natural units of time. Ancient peoples didn't need to count days when they could simply observe the moon's phases. The word month itself derives from moon in many languages. Archaeological evidence suggests that humans were tracking lunar phases at least 30,000 years ago. Bones and cave walls bear scratch marks that correspond to lunar cycles, perhaps the first calendars. A bone found in France, dating back perhaps 35,000 years, contains 29 marks that may represent a lunar month. These weren't mere artistic flourishes but practical tools, ways of measuring time, predicting the tides, knowing when animals might migrate or plants might fruit. The moon became embedded in human consciousness in profound ways. Nearly every ancient culture developed myths to explain the moon's existence and its changing phases. The Chinese spoke of Chang'e, who lives on the moon in eternal separation from her beloved. The Greeks knew Selene, who drove her silver chariot across the night sky. In Hindu tradition, the moon deity Chandra was born from the churning of the cosmic ocean. These weren't primitive misunderstandings but sophisticated attempts to encode astronomical knowledge in memorable story form. Ancient astronomers made remarkably precise observations of the moon. The Babylonians, 2,500 years ago, could predict lunar eclipses with surprising accuracy. They understood the Saros cycle, a period of approximately 18 years, 11 days, and 8 hours after which the pattern of eclipses repeats. The Greek philosopher Anaxagoras, in the 5th century BCE, correctly explained that the moon shines by reflected sunlight and that solar eclipses occur when the moon passes between Earth and Sunday. For this insight, among others, he was charged with impiety and exiled from Athens. The moon's influence on human physiology has been debated for millennia. The word lunatic derives from the Latin lunaticus, meaning moonstruck. Ancient Romans believed that the moon's phases could drive people to madness, and this belief persisted for centuries. While modern science has found no reliable evidence that the moon causes psychiatric episodes, the belief reveals something profound about humanity's perception of the moon's power over our minds and bodies. Yet there are real connections between the moon and biological rhythms. The most obvious is the ocean tide, which is primarily caused by the moon's gravitational pull. As Earth rotates beneath the moon, the water on the side facing the moon is pulled toward it, creating a bulge. Simultaneously, the water on the opposite side of Earth experiences less gravitational pull and creates another bulge. This creates 2 high tides and 2 low tides each day. The sun also contributes to tides, but because it's so much farther away, its tidal effect is only about 46% as strong as the moon's. These tides have profoundly shaped coastal ecosystems. Countless species time their reproduction to the tides. The grunion fish of California beaches swim ashore during the highest spring tides to lay their eggs in the sand, ensuring their offspring will have 2 weeks of protection before the next spring tide washes them out to sea. Coral reefs synchronize their spawning to the full moon, releasing eggs and sperm in massive underwater snowstorms of reproduction. These behaviors are genetically programmed responses to lunar cycles, refined over millions of years. Humans evolved in this tidal world, and some research suggests we retain subtle lunar rhythms in our biology. Studies have found slight variations in human sleep quality that correlate with the lunar cycle, with people sleeping an average of 20 minutes less and experiencing slightly lower sleep quality in the nights leading up to a full moon. This pattern is more pronounced in people without access to artificial light, suggesting our ancestors may have been more deeply entrained to lunar cycles. The mechanism isn't fully understood, but it may involve ancient light-sensing pathways in the brain that persist even when our eyes are closed. The human menstrual cycle's average length of 28 days is intriguingly close to the lunar month of 29.5 days, and many cultures have noted this coincidence. However, the relationship appears to be just that, a coincidence rather than causation. The menstrual cycle varies considerably between individuals and doesn't synchronize with moon phases in any systematic way that science has been able to detect. Yet the coincidence has been culturally significant, linking femininity with lunar symbolism across countless societies. What we do know is that the moon profoundly affects human perception and cognition in measurable ways. The presence of moonlight, even at its brightest during a full moon, which is about 400,000 times dimmer than sunlight, is enough to trigger specific responses in the human visual system. Our eyes contain two types of photoreceptor cells, rods and cones. Cones work in bright light and allow us to see color and fine detail. Rods are much more sensitive and allow us to see in dim conditions, but they provide only black and white vision. Under moonlight, we transition into what's called mesopic vision, a twilight realm where both rods and cones are partially active. Colors appear muted and strange. Blues and greens appear relatively brighter, while reds appear darker, a phenomenon called the Purkinje effect. This is why moonlit landscapes seem bathed in silvery blue, though moonlight itself is actually slightly yellow, being reflected sunlight bounced off the moon's gray surface. This transformation of visual perception under moonlight creates what researchers call the moon illusion, a phenomenon that has puzzled observers for thousands of years. When the moon rises on the horizon, it appears enormous, sometimes startlingly so. Yet when it's high in the sky later that night, it seems to have shrunk to a much smaller size. This isn't an optical effect. The moon's angular size in the sky is actually slightly smaller when it's on the horizon due to its greater distance from the observer. Instead, it's a perceptual illusion created by the brain's interpretation of size relative to foreground objects and the sky's apparent curvature. This illusion reveals something fundamental about how human brains construct reality. We don't experience the world directly but through neural models that make predictions based on context. The brain sees the moon near trees, buildings, and mountains and interprets it as a distant object that must be enormous to appear so large. When the moon is high in the empty sky with no reference points, the brain has no context for size, and it appears smaller. The raw sensory data hasn't changed, only the brain's interpretation. This interpretive nature of perception becomes even more fascinating when we consider how the moon affects human attention and awareness. Research in cognitive psychology has found that the full moon significantly increases the amount of ambient light at night, which can affect melatonin production in the brain. Melatonin, produced by the pineal gland, is the neurochemical that regulates our circadian rhythm and induces sleepiness. Even small amounts of light can suppress melatonin production, and the full moon provides enough illumination to create measurable, though modest, effects. the pineal gland itself has a fascinating evolutionary history. In some ancient vertebrates, it was actually a third eye, a light-sensitive organ on the top of the head. Some modern reptiles, like the tuatara of New Zealand, still possess this so-called parietal eye. In mammals, including humans, the pineal gland has lost its direct light-sensing capability but remains exquisitely sensitive to light information transmitted from the eyes via a neural pathway. This ancient connection between light and brain function means that the moon, in its monthly cycle of brightness, still whispers to the most primitive parts of our nervous system. The moon's gravitational effect on the human body has also been a subject of speculation. Since human bodies are roughly 60% water, could the moon create biological tides within us? The physics provides a clear answer: no. While the moon's gravity does affect the water in our bodies, the effect is infinitesimally small. The moon creates a tidal force by pulling more strongly on the side of Earth nearest to it than on the far side. But a human body is so small compared to Earth that there's virtually no difference in the moon's gravitational pull across the few feet of our bodies. The gravitational effect of a nearby mosquito on your body is stronger than the moon's differential tidal force. Yet the moon's influence on human culture and psychology cannot be measured in gravitational units alone. Throughout history, the moon has served as a canvas for human imagination, a mirror reflecting our dreams, fears, and aspirations. When ancient astronomers like Galileo Galilei first turned telescopes toward the moon in 1609, they discovered a world of mountains, valleys, and craters. This revelation was revolutionary, showing that the heavens were not perfect and unchanging but rugged and Earth-like. The moon had geography. Those craters, we now understand, are the scars of billions of years of cosmic bombardment. The moon's surface is a museum of solar system history, preserving a record of impacts that would have been erased on Earth by erosion, tectonics, and life itself. Each crater tells a story of violence, of asteroids and comets crashing down at speeds of many miles per second, releasing energy equivalent to nuclear weapons. The largest visible crater, the South Pole Aitken Basin, is over 1,500 miles across and 8 miles deep, created by an impact so massive it nearly shattered the moon. The dark patches visible on the moon's face, which various cultures have interpreted as a rabbit, a face, a woman, or other figures, are actually vast plains of solidified lava called Maria, the Latin word for seas. Early astronomers, seeing these smooth dark regions, imagined them to be bodies of water. In reality, they formed billions of years ago when massive impacts cracked through the lunar crust, allowing molten rock from the interior to flood across the surface. This volcanism has long since ceased. The moon is now geologically dead, its interior having cooled below the point where magma can form. This geological death means the moon changes very slowly now. The footprints left by Apollo astronauts in 1969 will likely remain visible for millions of years, barring a direct meteor strike. There's no wind or rain to erase them, no life to disturb them. They're monuments to human achievement, preserved in the lunar dust, gradually being covered by micrometeorite impacts so tiny that it will take eons for them to disappear. When Neil Armstrong and Buzz Aldrin became the first humans to walk on the moon on July 20th, 1969, they fulfilled a dream humans had harbored since we first looked up at the night sky. Their journey was made possible by understanding orbital mechanics, the mathematical description of how gravity shapes motion in space. The moon orbits Earth in an ellipse, not a perfect circle, ranging from about 225,000 miles at its closest approach to about 252,000 miles at its farthest. This variation causes the moon's apparent size in the sky to change by about 14% between its closest and farthest points, though this change is difficult to notice without careful measurement. The moon's orbit is also tilted about 5 degrees relative to Earth's orbit around the sun. This tilt is why we don't have solar and lunar eclipses every month. For an eclipse to occur, the sun, Earth, and moon must align along the line where the moon's orbit crosses Earth's orbital plane, called the nodes. This alignment happens only occasionally, creating eclipse seasons twice per year when these cosmic conditions are just right. During a total lunar eclipse, when Earth's shadow falls across the moon doesn't go completely dark but glows a deep red. This is because Earth's atmosphere bends and filters sunlight around our planet's edge. Blue light scatters away, the same process that makes our sky blue during the day, while red light passes through and illuminates the moon. Every lunar eclipse is lit by all the sunrises and sunsets happening on Earth at that moment, painted across the moon's face. Solar eclipses create an even more spectacular phenomenon. The sun is about 400 times larger than the moon, but it's also about 400 times farther away. This cosmic coincidence means both objects appear almost exactly the same size in Earth's sky, allowing the moon to precisely cover the sun during a total solar eclipse. This perfect match is temporary in cosmic time. The moon is gradually receding from Earth, and in about 600 million years, it will be too far away to completely cover the sun. Total solar eclipses will become impossible, and future creatures, if any exist to observe, will never experience the spectacular moment of totality that we can witness today. During totality, the sun's corona, its outer atmosphere, becomes visible as a pearly white halo around the darkened moon. The temperature drops, stars appear in the daytime sky, and animals become confused, birds returning to roost as if night has fallen. For ancient peoples who didn't understand the celestial mechanics, eclipses were terrifying, interpreted as omens, divine anger, or cosmic monsters devouring the sun. Many cultures developed elaborate rituals to protect themselves during eclipses or to free the sun or moon from whatever was attacking it. The Apollo missions brought back 842 pounds of moon rocks, and these samples revolutionized our understanding of lunar and terrestrial history. Chemical analysis revealed that the moon's composition is remarkably similar to Earth's mantle, supporting the giant impact hypothesis of the moon's formation. These rocks contain no water and no organic compounds, having formed in the violence of the impact that created the moon, where temperatures exceeded thousands of degrees. Yet recent discoveries have complicated this picture. Spacecraft observations have detected water ice in permanently shadowed craters near the moon's poles, where temperatures never rise above -250 degrees Fahrenheit. This ice may have been delivered by comet impacts over billions of years, accumulating in these eternal cold traps. For future lunar exploration, this ice could be invaluable, providing not just drinking water but also hydrogen and oxygen that could be split electrolytically to create rocket fuel. The moon's far side, often incorrectly called the dark side, remains mysterious. Due to tidal locking, the same process that has slowed the moon's rotation until it shows only one face to Earth, we never see the far side from our planet. It wasn't until 1959, when the Soviet spacecraft Luna 3 flew around the moon, that humans first saw this hidden hemisphere. It looks strikingly different from the near side, with almost no maria, much thicker crust, and more rugged terrain. Why the two hemispheres differ so dramatically remains a subject of scientific investigation, possibly related to Earth's gravitational influence during the moon's formation or to the distribution of radioactive elements that kept the near side hotter and more volcanically active. This tidal locking is itself a testament to the deep connection between Earth and Moon. Early in the Moon's history, it rotated much faster, but Earth's gravity created tidal bulges in the Moon's solid body, just as the Moon creates tides in Earth's oceans. These bulges experienced friction as the Moon rotated beneath them, gradually slowing the Moon's rotation. Eventually, the Moon's rotation period matched its orbital period, reaching a stable configuration where it always shows the same face to Earth. Earth is experiencing the same process in reverse. The Moon's tidal forces are slowing Earth's rotation, lengthening our days by about 1.7 milliseconds per century. 400 million years ago, in the Devonian period when fish were first crawling onto land, an Earth day was only about 22 hours long. The Moon was closer, and tides were stronger. As life evolved on those ancient shorelines, the rhythm of stronger tides may have influenced the evolution of the first land animals. Some scientists have speculated that the twice-daily tidal cycle might have influenced the evolution of our circadian rhythm, our internal biological clock that runs on an approximately 24-hour cycle, though this remains speculative. What we do know is that circadian rhythms are fundamental to human brain function. The suprachiasmatic nucleus, a tiny region of the hypothalamus containing only about 20,000 neurons, serves as the brain's master clock. This clock is synchronized, or entrained, primarily by light exposure, particularly blue light that signals daytime. Before artificial lighting, the strongest sightgiver, or time giver, was the sun, but the moon provided secondary timing information, especially its monthly cycle from new to full and back. Research has shown that people living in environments without artificial light, such as traditional hunter-gatherer communities, naturally adjust their sleep patterns with the lunar cycle. They tend to go to bed later and sleep less in the nights before the full moon, when evening light is brightest, and sleep more during the new moon, when nights are darkest. This pattern suggests that human circadian rhythms retain some capacity to respond to lunar cycles, even though this sensitivity has been largely overridden by electric lighting in modern life. The psychological impact of the moon on human consciousness extends beyond measurable biological rhythms. The moon has inspired more poetry, music, and art than perhaps any other natural object. There's something about its presence, its reliability amid life's changes, that speaks to the human psyche. The moon is often associated with femininity, emotion, dreams, and the unconscious mind in contrast to the sun's masculine, rational, conscious associations. These archetypal connections appear across diverse cultures, suggesting they tap into something fundamental about human psychology. Carl Jung, the Swiss psychiatrist who founded analytical psychology, wrote extensively about the moon as a symbol in dreams and myths. He saw it as representing the anima, the feminine aspects of the male psyche, and more broadly as a symbol of the unconscious mind itself. The moon's changing phases mirror the cycles of psychological life, the rhythm of mood, creativity, and insight. Whether these Jungian interpretations reflect objective truth or simply our tendency to find meaning in patterns, they demonstrate how deeply the moon is woven into human self-understanding. Modern neuroscience has begun to explore how symbolic associations like these are encoded in the brain. When we see the moon, multiple neural networks activate simultaneously. Visual cortex processes the shape and brightness. The hippocampus retrieves memories associated with the moon. The amygdala adds emotional coloring based on past experiences and cultural conditioning. Language centers access the word moon and its semantic associations. All of this happens in milliseconds, creating the rich, multifaceted experience of seeing the moon. This neural complexity means that the moon can trigger different responses in different people based on their experiences and cultural background. For someone who shared romantic moments under the moon, its appearance might activate reward circuits and generate feelings of nostalgia or longing. For someone who learned childhood stories about the moon's power, it might activate circuits related to awe or mystery. The physical moon in the sky is the same, but the psychological moon is different for each observer. This subjectivity of experience doesn't diminish the moon's objective reality but enriches it. The moon is simultaneously a large natural satellite orbiting Earth at a specific distance with measurable physical properties, and a symbol, a mirror, a canvas for human meaning-making. Both perspectives are valid and necessary for understanding the full relationship between the moon and human consciousness. As you lie here now, relaxing into sleep, the moon is following its ancient path across the sky. It's moving at about 2,288 miles per hour in its orbit around Earth, though from your perspective, it seems to drift slowly westward as Earth rotates beneath it. Photons of sunlight are bouncing off the moon's surface, traveling the roughly 240,000 miles to Earth in about 1.3 seconds, some of them perhaps entering through your window, carrying the same soft light that illuminated the paths of your distant ancestors. The moon you see tonight is the same moon that was watched by Cleopatra and Julius Caesar, by the builders of Stonehenge, by the painters who decorated the caves of Lascaux. It has been humanity's constant companion, a reminder that we are part of something larger than ourselves, connected to cosmic forces in deep time. The moon teaches patience, showing us that changes can be profound even when they're gradual, that cycles are natural, that distance doesn't erase connection. In its monthly journey from new moon to full and back, the moon demonstrates impermanence without loss. It doesn't disappear during the new moon, it's simply hidden, preparing to emerge again. This cycle has comforted humans facing loss and change for millennia. Just as the moon returns, so too does opportunity, hope, and renewal. Scientists continue to discover new aspects of the moon's influence on Earth. Recent studies suggest that the moon's gravitational pull may affect tectonic activity, possibly triggering earthquakes when its tidal stress adds to other geological forces. The moon may have protected Earth from additional large impacts by gravitationally deflecting some asteroids that would otherwise have struck our planet. Every discovery reveals new threads in the intricate web connecting Earth and its satellite. Looking forward, the moon represents humanity's next frontier in space exploration. Plans are underway for permanent lunar bases, using the moon as a testing ground for technologies needed for Mars missions and as a platform for astronomical observations. The far side of the moon, shielded from Earth's radio noise, would be an ideal location for radio telescopes that could observe the universe in frequencies impossible to detect from Earth. But perhaps the moon's greatest gift to humanity is the perspective it provides. The famous Earthrise photograph, taken by Apollo 8 astronauts in 1968, showing Earth rising above the moon's horizon, transformed how humans see themselves. Our planet appeared as a small, fragile, blue and white sphere in the cosmic darkness, the only known world harboring life, seen from a perspective once impossible to imagine. That image, made possible by reaching the moon, helped spark the environmental movement and a new appreciation for Earth's uniqueness and vulnerability. As you sink deeper into rest, let your mind drift with the moon's gentle light. Imagine its pull, not as force but as connection, the same gravity that moves oceans also acknowledging your presence, though you're too small to notice. You are part of this cosmic dance, a brief moment of consciousness in a universe of matter and energy, held gently by gravity to a planet that's held by a star, accompanied through space by a moon that has witnessed the entire story of life on Earth. The moon will continue its journey tonight and tomorrow night and all the nights to come. It will wax toward fullness, then wane toward darkness, then begin again, as it has for more than 4 billion years. In this reliability, there is comfort. In its beauty, there is inspiration. In its distance, there is mystery. In its presence, there is companionship. Let the moon's ancient light carry your thoughts gently away, knowing that when you wake, it will still be there, continuing its eternal dance around our world, linking past and future, earth and sky, science and wonder, consciousness and cosmos. Rest now, held in the same gravitational embrace that holds the moon, part of the same universe, watching over you as you sleep. The moon, faithful companion to our lonely planet, keeps watch through the night. As has it always done. As it always will. Sleep well, under the moon's silver gaze, connected to all who have ever looked up in wonder at the night sky. Sleep well. The moon's surface, that ancient canvas you see glowing in the night, holds secrets written in a language of light and shadow. When sunlight strikes the lunar surface at different angles throughout the month, it reveals textures invisible to us during the full moon's flat illumination. Near the terminator, the boundary between lunar day and night, shadows stretch long across the landscape, making crater walls and mountain peaks stand in sharp relief. This is why astronomers often prefer observing the moon when it's not full, when the play of light and shadow reveals the three-dimensional complexity of its terrain. The composition of lunar soil, called regolith, is unlike anything found naturally on Earth. Over billions of years, meteorite impacts have pulverized the moon's surface rocks into a fine powder, mixed with tiny glass beads created when impacts melted and instantly cooled lunar material. This regolith is surprisingly sharp and abrasive, as there's no wind or water to smooth its edges. Apollo astronauts discovered it could work its way into everything, damaging equipment and even penetrating their spacesuits' multiple layers. Harrison Schmitt, the only geologist to walk on the moon, experienced lunar dust hay fever, sneezing and experiencing nasal irritation from the microscopic particles. This regolith tells stories of the sun itself. Solar wind, the stream of charged particles constantly flowing from our star has been implanted into lunar soil grains for billions of years. Scientists studying Apollo samples discovered helium-3, a rare isotope on Earth but relatively abundant in lunar regolith due to this solar wind bombardment. Helium-3 could potentially fuel future nuclear fusion reactors without producing radioactive waste, making the moon a possible energy resource for humanity's distant future. Each grain of moon dust is a tiny time capsule, recording the sun's output across geological ages. The moon's relationship with Earth's magnetic field reveals another fascinating connection. Earth generates a magnetic field through the dynamo effect in its liquid iron core, and this field extends far into space, creating a protective bubble called the magnetosphere. The moon passes through Earth's magnetotail, the elongated part of the magnetosphere that stretches away from the sun, for several days each month. During this time, Earth's magnetic field partially shields the moon from solar wind, and the lunar surface becomes electrically charged in complex ways. This charging can cause dust particles to levitate slightly above the surface, creating a thin, temporary atmosphere of hovering dust. Speaking of atmosphere, the moon does have one, though calling it an atmosphere stretches the definition. It's so tenuous that it's better described as an exosphere, containing only about 100,000 molecules per cubic centimeter compared to Earth's atmosphere at sea level, which contains about 25 quintillion molecules in the same space. This trace atmosphere consists of elements like sodium, potassium, argon, and helium, sourced from solar wind, radioactive decay, and meteorite impacts. It's far too thin to transmit sound or support any form of life, and it's so insubstantial that individual atoms rarely collide with each other. In this near-perfect vacuum, an astronaut's footprint creates a tiny puff of dust that follows ballistic trajectories back to the surface, each particle moving like a tiny spacecraft in the moon's weak gravity. That weak gravity, just 1/6 of Earth's, creates the graceful, bounding movements you've seen in footage of astronauts on the moon. A person weighing 180 pounds on Earth would weigh only 30 pounds on the moon. This reduced gravity means you could jump 6 times higher on the moon than on Earth, though you'd fall back down in slow motion, taking the same amount of time for the jump because both your upward and downward motion would be slower. The muscles that evolved to move you through Earth's gravity would give you almost superhuman abilities on the moon, though astronauts found that the bulky spacesuits limited their actual mobility considerably. The moon's low gravity has profound implications for its geological history. With less gravitational compression, the moon's interior never became as hot and active as Earth's. While Earth has maintained a liquid outer core that generates our magnetic field, the moon's core cooled and solidified within its first billion years. The moon did once have a magnetic field, evidence preserved in magnetized lunar rocks, but this field faded away as the lunar dynamo shut down. Without this protective magnetic field, the solar wind has directly struck the lunar surface for billions of years, gradually altering its chemistry and contributing to the formation of that unique regolith. Crater formation on the moon provides a window into the violent history of the solar system. When an asteroid or comet strikes the moon at speeds ranging from 12 to 45 miles per second, it releases kinetic energy in a fraction of a second. The impactor vaporizes instantly, and a shock wave propagates through the lunar crust, excavating material and throwing it outward in a spectacular splash pattern. The larger impacts create central peaks when the compressed rock rebounds after the initial impact, like the splash you see when a drop falls into water, but frozen in stone. Some of the largest craters show multiple concentric rings, created by seismic waves rippling through the lunar crust like frozen ripples on a pond. These impact craters follow mathematical patterns that reveal solar system history. Small craters vastly outnumber large ones, following a power law distribution that reflects the size distribution of asteroids and comets. The density and degradation of craters in different regions allows scientists to estimate relative ages of lunar surfaces. The heavily cratered lunar highlands are ancient, dating back over 4 billion years to the late heavy bombardment, a period when the inner solar system was swept by a storm of impacts. The smoother, darker Maria are younger, formed between 3.1 and 3.8 billion years ago when massive impacts created basins that later filled with lava. The Moon's influence on Earth's ocean tides follows predictable mathematical patterns discovered by Isaac Newton and refined by later scientists. The tidal force isn't uniform across Earth but varies with the inverse cube of distance. This means that tidal forces decrease very rapidly with distance. The side of Earth facing the Moon experiences the strongest gravitational pull, the Earth's center experiences moderate pull, and the far side experiences the weakest pull. This differential force creates the two tidal bulges. When the Sun, Moon, and Earth align during full and new moons, their gravitational forces combine to create spring tides, which are especially high. When the Sun and Moon are at right angles during the first and third quarters, they partially cancel each other out, creating neap tides, which have the smallest range. The energy that drives these tides comes from Earth's rotation. As our planet spins beneath the tidal bulges, friction between moving water and the ocean floor converts rotational energy into heat. This is why Earth's rotation is slowing and why the Moon is gradually moving away. The Moon's orbital energy increases as it recedes, gaining altitude in a beautiful demonstration of conservation of angular momentum. This same process has already slowed the Moon's rotation to match its orbital period, making it tidally locked. Tidal forces have shaped solar system bodies throughout cosmic history. Jupiter's moon Io experiences such intense tidal heating from Jupiter's enormous gravitational field that it's the most volcanically active body in the solar system, with hundreds of active volcanoes constantly resurfacing the world. Saturn's moon Enceladus has geysers of ice and water vapor erupting from its south pole, powered by tidal friction. Even Jupiter and Saturn themselves are slightly egg-shaped due to their own rotation and the tidal forces from their many moons. Tides are a fundamental force sculpting worlds wherever gravity acts on extended bodies. The Moon's orbit around Earth isn't simple but involves complex perturbations from the Sun's gravity and the non-spherical shape of Earth. Ancient astronomers cataloged these variations with painstaking precision. The Moon's orbital plane precesses, meaning it rotates like a wobbling plate, completing one full precession every 18.6 years. This cycle, known as the lunar nodal precession, affects tidal patterns and was understood by ancient peoples who lived close to the sea. The Babylonians incorporated it into their eclipse predictions. The Moon's elliptical orbit also precesses, meaning the point of closest approach rotates around Earth, completing one cycle every 8.85 years. These orbital complexities mean the Moon's distance from Earth varies significantly. At perigee, its closest approach, the Moon is about 225,623 miles from Earth. At apogee, its farthest point, it's about 252,088 miles away. This difference of about 26,000 miles might not seem like much compared to the total distance, but it means the Moon appears about 14% larger and 30% brighter at perigee than at apogee. When a full moon occurs at or near perigee, it's sometimes called a supermoon in popular culture, though astronomers don't generally use this term. These supermoons do create slightly higher tides, but the difference is only a few inches, much less dramatic than popular media sometimes suggests. The moon's gravitational influence extends beyond tides to affect Earth's shape itself. Our planet isn't a perfect sphere but an oblate spheroid, slightly flattened at the poles and bulging at the equator due to its rotation. Additionally, the moon's gravity creates a permanent tidal deformation in Earth's solid body. The rocky Earth rises and falls by about 12 inches twice daily as the moon passes overhead, though we don't notice because everything around us rises and falls together. This solid Earth tide can be measured with sensitive instruments and must be accounted for in precision GPS systems and gravitational studies. The concept of the moon's phases, so familiar it seems simple, actually involves a beautiful interplay of geometry and perspective. The moon doesn't generate light but reflects sunlight, and it's always half illuminated by the sun. What changes is our viewing angle on that illuminated hemisphere. During new moon, the illuminated side faces away from Earth, and we see only the dark side. As the moon orbits, we gradually see more of the illuminated side, waxing through crescent, first quarter, when we see half, and gibbous phases to full moon, when the entire near side is illuminated. Then the process reverses, waning back to new. This monthly transformation affected how ancient cultures organized time and religious observance. The Islamic calendar is purely lunar, with months beginning at the first sighting of the crescent moon after new moon. The Jewish and Chinese calendars are lunisolar, incorporating both lunar months and solar years through complex intercalation. The Christian holiday of Easter is calculated based on the first full moon after the spring equinox, a formula established at the Council of Nicaea in 325 CE. These calendar systems are more than practical timekeeping. They embedded humanity's observation of the moon into the structure of society and consciousness. The moon also served as an early testing ground for mathematical astronomy. Greek astronomers, particularly Aristarchus of Samos around 270 BCE, attempted to calculate the distances to the moon and sun using geometric methods. Aristarchus observed that during half moon, the angle between the sun and moon as seen from Earth was nearly a right angle. From this observation and some assumptions, he estimated that the sun was about 19 times farther than the moon, an underestimate but a remarkable achievement given his tools. He also attempted to measure the moon's size by timing lunar eclipses, reasoning that the time the moon took to pass through Earth's shadow would reveal its size relative to Earth. More accurate measurements came much later. In the 1750s, astronomers used the transit of Venus to triangulate the distance to the Sun, which then allowed calculation of the moon's distance through its orbital period using Kepler's laws. These measurements revealed that the moon is about 1/4 Earth's diameter, making it unusually large relative to its planet. Most moons in the solar system are tiny compared to their host planets. Mars's two moons, Phobos and Deimos, are just a few miles across. Even Jupiter's four large Galilean moons are small compared to Jupiter itself. Only Pluto's moon Charon rivals our moon in being proportionally large relative to its primary, which is one reason some astronomers consider Pluto and Charon a double dwarf planet system. lies about 2,900 miles from Earth's center, still within Earth but about 1,100 miles beneath the surface. Both Earth and Moon orbit this common center of mass, though because Earth is so much more massive, 81 times the Moon's mass, Earth's orbit around the barycenter is much smaller than the Moon's. Still, if you could view the Earth-Moon system from far away, you'd see Earth wobbling slightly as both bodies orbit their common center. The Apollo program's scientific legacy extends far beyond the rock samples. Astronauts deployed seismometers on the lunar surface that operated for years, recording moonquakes. These revealed that the Moon experiences seismic activity, though far less than Earth. There are 4 types of moonquakes: deep moonquakes about 435 miles below the surface, caused by tidal stresses from Earth; thermal moonquakes caused by the expansion of the frigid lunar crust when sunlight returns after the 2-week lunar night; meteorite impact vibrations; and shallow moonquakes, the most dramatic, which can reach 5.5 on the Richter scale and last for over 10 minutes due to the lack of water and lunar rocks to dampen the vibrations. Seismic data revealed the Moon's internal structure. Like Earth, the Moon has a crust, mantle, and core, though the proportions are different. The lunar crust averages about 30 miles thick on the near side and 50 miles thick on the far side, this asymmetry being one of the Moon's enduring mysteries. The mantle extends down to about 900 miles deep. At the center lies a small iron core, only about 150 miles in radius, which is solid or perhaps partially molten. This small core explains why the Moon's density is lower than Earth's, only 3.34 grams per cubic centimeter compared to Earth's 5.52. The Moon contains a smaller proportion of heavy elements, consistent with it having formed from Earth's outer layers after the Theia impact. The lunar samples also revealed the concept of lunar meteorites here on Earth. While we've sent missions to retrieve Moon rocks, the Moon has also sent samples to Earth naturally. Powerful asteroid impacts on the Moon can accelerate rocks to speeds exceeding the Moon's escape velocity of 1.5 miles per second, launching them into space. Some of these eventually fall to Earth as meteorites. Over 650 lunar meteorites have been identified so far, distinguished by their unique chemistry and mineral composition that matches Apollo samples. These provide free samples from parts of the Moon we've never visited, including the far side. Similarly, Earth rocks have been found on the Moon. The Genesis rock, collected by Apollo 15 astronauts, was initially thought to be primordial lunar crust, but some researchers now believe it might actually be a piece of Earth, ejected by a powerful impact billions of years ago and eventually landing on the Moon. Earth and Moon have been exchanging material throughout their shared history, a cosmic correspondence of stone. The temperature variations on the Moon are extreme due to the lack of atmosphere. During the lunar day, which lasts about 2 Earth weeks, surface temperatures in direct sunlight can reach 260 degrees Fahrenheit, hot enough to boil water. During the equally long lunar night, temperatures plummet to minus 280 degrees Fahrenheit, cold enough to freeze carbon dioxide. This 540-degree temperature swing is among the most extreme in the solar system. Equipment operating on the Moon must be designed to survive these brutal conditions, and future lunar habitats will require sophisticated thermal management systems. These temperature extremes have shaped the Moon's surface in subtle ways. Thermal expansion and contraction over billions of day-night cycles have contributed to weathering lunar rocks, creating some of the regolith through a process called thermal fatigue. The Moon's surface is also affected by space weathering, where solar wind and cosmic rays gradually alter the chemistry and color of exposed rocks. fresh craters appear bright because they've excavated material from below the weathered surface. Over millions of years, these bright craters darken as space weathering catches up, allowing scientists to estimate crater ages from their brightness. The phenomenon of libration allows us to see slightly more than half of the moon's surface over time, even though it's tidally locked. Libration is an actual rotation but apparent wobbling caused by several factors. The moon's orbit is elliptical, so it moves faster at perigee and slower at apogee, but its rotation rate is constant. This means we can see a bit farther around the eastern or western edge at different times, called longitudinal libration. The moon's orbital plane is also tilted relative to its equator, allowing us to peek over the North Pole at some times and the South Pole at others, called latitudinal libration. Additionally, since we observe from Earth's surface rather than its center, our position changes as Earth rotates, creating diurnal libration. Combined, these effects allow us to see about 59% of the lunar surface from Earth, leaving 41% permanently hidden from our view. That permanently hidden far side remained a complete mystery until the space age. Soviet Luna 3 spacecraft's photographs in 1959 revealed a surface strikingly different from the familiar near side. The question of why the two hemispheres differ so dramatically involves the moon's thermal history. One hypothesis suggests that Earth's gravity created tidal heating in the young moon, but this heating was concentrated on the near side facing Earth. This kept the near side's crust thinner and more prone to volcanism, allowing lava to flood the impact basins and create the Maria. The far side, cooler and with thicker crust, couldn't support the same level of volcanism, so its impact basins remained unfilled, leaving the far side heavily cratered and mountainous. The moon's influence on human sleep patterns extends beyond light exposure. Some research suggests that human sleep architecture, the pattern of sleep stages throughout the night, shows subtle variations with the lunar cycle. Sleep consists of cycling through stages: light sleep, deep sleep, and REM sleep where dreaming occurs. Some studies have found that deep sleep decreases and REM latency increases around the full moon, even in controlled laboratory settings without windows. The mechanism remains unclear, but it might involve ancient evolutionary programming that kept our ancestors more alert during bright nights when predators could hunt more easily. This possible lunar influence on sleep connects to the broader field of chronobiology, the study of biological rhythms. Circadian rhythms, running on approximately 24-hour cycles, are the best known. But organisms also exhibit ultradian rhythms shorter than a day, and infradian rhythms longer than a day. Some organisms show clear circulunar rhythms, approximately monthly cycles synchronized to the moon. While humans don't have the robust lunar rhythms seen in marine animals, subtle influences may persist in our biology. Evolutionary echoes from ancestors who lived more directly under the sky. The psychology of the moon extends to its symbolic role in language and metaphor. We speak of honeymoons for newlywed couples, originally referring to the first month of marriage, sweet but waning like the moon. Someone over the moon is extremely happy, elevated to celestial heights. To moon about means to behave dreamily or aimlessly, as if dazed by moonlight. These expressions reveal how deeply the moon has penetrated human culture and thought, becoming shorthand for particular emotional and psychological states. The moon appears in dreams with remarkable frequency, analyzed by psychologists as representing various aspects of the dreamer's psyche. Unlike the sun, which typically symbolizes consciousness and clarity in dream interpretation, the moon often represents the unconscious, hidden aspects of self, or emotions that ebb and flow. The particular phase of the moon in a dream might carry meaning. A full moon might represent completeness or revelation. A new moon might suggest new beginnings or the unknown, and a waning moon might indicate letting go or loss. Whether these interpretations reflect universal truths or cultural conditioning, they demonstrate the moon's role as a canvas for human meaning-making. Modern light pollution has dimmed the moon's cultural presence for many people. In cities, the night sky glows with artificial light, and the moon often struggles to compete with streetlights and illuminated buildings. Studies have shown that over 80% of humanity now lives under light-polluted skies, and over 1/3 of people cannot see the Milky Way from their homes. The moon remains visible, but its psychological impact is reduced when it's just one light among thousands rather than the undisputed ruler of the night sky. This loss of dark skies represents a disconnection from natural cycles that shaped human evolution. For hundreds of thousands of years, humans lived intimately with the moon's monthly cycle. Its phases determined when to travel, hunt, or gather. It served as the night's natural calendar and clock. This relationship has been largely severed in just a few generations, an evolutionary blink. Some researchers suggest this disconnection from natural light cycles contributes to the epidemic of sleep disorders in modern society, as our circadian systems evolved expecting bright days and truly dark nights punctuated by moonlight, not the constant twilight of urban environments. Reconnecting with lunar observation has therapeutic potential. Mindfulness practices often incorporate attention to natural cycles, including moon phases. The simple act of stepping outside each night to note the moon's appearance, its phase and position, can create a sense of connection to something larger and slower than daily concerns. This practice has been recommended by some therapists as a way to reduce anxiety and gain perspective, reminding us that our urgent problems exist within larger rhythms of time. The moon's role in navigation extends beyond its use as a night light. The moon's position against the background stars changes predictably, and skilled navigators could use lunar observations to determine time and even longitude before accurate clocks were invented. The method of lunar distances, measuring the angle between the moon and specific stars, allowed sailors to calculate time with sufficient accuracy for oceanic navigation. This technique was crucial for maritime exploration and trade from the 1700s until chronometers became reliable and affordable in the 1800s. Indigenous cultures around the world developed sophisticated lunar observations for practical purposes. Many Native American tribes named full moons according to seasonal events: the wolf moon in January when wolves howled outside camps, the strawberry moon in June when strawberries ripened, the harvest moon, the full moon closest to the autumn equinox, when its light allowed farmers to work late harvesting crops. These names encoded ecological knowledge, linking celestial observation with practical survival information. The moon's future is as fascinating as its past. Billions of years from now, the moon will continue receding until it reaches a distance where its orbital period matches Earth's length and day, perhaps taking about 47 current days. At that point, tidal locking will be mutual. The moon will orbit Earth in the same time Earth takes to rotate, so the moon will hover over one spot on Earth, always visible from one hemisphere and never visible from the other. Earth and Moon will face each other eternally like cosmic dance partners in a frozen embrace. However, this future state will never actually be reached because the Sun will have evolved into a red giant long before then, likely engulfing both Earth and Moon about 5 billion years from now. In the nearer future, the Moon beckons as humanity's next home beyond Earth. Unlike Mars, the Moon is only 3 days away by spacecraft, allowing relatively quick response times for emergencies and regular supply missions. Lunar bases could serve multiple purposes: mining helium-3 and other resources, manufacturing using lunar materials, astronomical observatories on the far side shielded from Earth's radio noise, and as a stepping stone for missions deeper into the solar system. Launching spacecraft from the Moon's low gravity is much easier than launching from Earth, potentially making lunar orbit a staging area for Mars missions. The challenges of lunar colonization are substantial. The lack of atmosphere means habitats must be completely sealed and pressurized. Radiation from the Sun and cosmic rays poses health risks, requiring habitats to be built underground or shielded with lunar regolith. The sharp, abrasive dust will infiltrate everything, potentially causing equipment failures and health problems. The lunar day-night cycle of 2 weeks of sunlight followed by 2 weeks of darkness complicates solar power systems. Water, air, and food must be supplied from Earth or produced locally through challenging processes. Yet these challenges are solvable with existing or near-term technology. Water ice in polar craters could be mined and purified. Oxygen can be extracted from lunar regolith through various chemical processes, as silicon dioxide, the main component of lunar soil, is nearly half oxygen by mass. Solar panels and batteries could provide power, supplemented by nuclear reactors for the long lunar night. Habitats could be 3D printed using lunar regolith as a building material, leveraging local resources to reduce what must be transported from Earth. Hydroponics could grow food in pressurized greenhouses, taking advantage of continuous sunlight in some polar regions where the sun barely dips below the horizon. As you rest now, breathe slowly and deeply, the Moon continues its patient work. It's pulling gently on Earth's oceans, creating tidal currents that circulate nutrients and support marine ecosystems. It's stabilizing Earth's axial tilt, maintaining the moderate seasons that allowed human civilization to flourish. It's gradually slowing Earth's rotation, lengthening our days by imperceptible amounts, banking angular momentum in its receding orbit. All of this happens whether anyone watches or not, a cosmic mechanism running since before life existed, continuing long after any individual consciousness fades. The Moon teaches us about time itself. Human lives are brief flashes measured against lunar time. The Moon you see is ancient beyond human comprehension, yet young in cosmic terms. It has witnessed the entire story of life on Earth, from the first microscopic cells appearing in ancient seas to the present moment of your awareness, reading these words, thinking about the Moon. Your moment of consciousness is infinitesimally brief in the Moon's story, yet it's also part of that story, one more awareness joining billions of others across time who have looked up and wondered. In wondering about the Moon, humans have developed science itself. The quest to understand the Moon's motion led to Newton's laws of motion and universal gravitation. Studying moonlight led to understanding the electromagnetic spectrum. Reaching the Moon required developing rocket science, computer technology, materials science, and countless other fields. The moon has been a teacher, posing questions that forced us to expand our knowledge, driving human intellectual development simply by existing, by raising its face each night and asking, "What am I? How did I come to be? Can you reach me?" And we reached it. On July 20th, 1969, humans stood on another world for the first time, fulfilling a dream as old as consciousness itself. That achievement represents something profound about human nature, this drive to explore, to understand, to reach beyond our grasp. The moon inspired this drive for millennia, always visible, seemingly close, yet impossibly far by any means our ancestors could imagine. It represented the boundary between the attainable and the impossible, and we crossed that boundary. The 12 humans who have walked on the moon, all between 1969 and 1972, experienced something no language can fully capture. They saw Earth from the moon's surface, a blue and white jewel hanging in the black sky, the only color in a monochrome landscape of gray dust and black space. They experienced the profound silence of a world without air, where sound cannot travel. They felt the strange lightness of lunar gravity and the cumbersome weight of spacesuits. They returned changed, struggling to articulate the spiritual dimensions of their experience, often describing it in terms usually reserved for religious or mystical experiences. These experiences point to something important about consciousness and perspective. Seeing Earth from the moon, we see ourselves differently. The political boundaries that seem so important, the conflicts that consume our attention, the divisions we create between us and them, all of these vanish when viewed from lunar distance. There is only one Earth, one incredibly improbable oasis of life, one home for all humanity. The moon gave us the perspective to see this truth, not as an abstract idea but as a visceral, undeniable fact. So as you drift towards sleep, carry this perspective with you. You are lying on a planet that is accompanied by a moon, orbiting a star, in a galaxy among billions. This particular arrangement of matter has given rise to your consciousness, your thoughts, your experience of being. The moon above connects you to deep time, to the formation of the solar system, to the story of life itself. Its light connects you to every human who has ever lived, who has looked up and felt the same sense of wonder you feel now. Let that wonder be a lullaby. Let the moon's ancient patient light soothe your thoughts. Rest in the knowledge that the cosmos is vast, time is long, and your moment of awareness, however brief, is part of something grand and mysterious. The moon will still be there tomorrow night, and the night after that, constant companion to Earth, silent witness to life's great experiment. Sleep now, under the moon's watchful gaze, held by gravity to your home world, connected to all things through the same physical laws that guide the moon's orbit. Sleep, and let your dreams drift through silver moonlight, through the spaces between stars, through the quiet wonder of existence itself. The moon keeps its vigil, as it always has, as it always will, until the far future when the sun expands and the moon's long story finally ends. But that is so far away as to be meaningless. Tonight, now, the moon is here. Beautiful, mysterious, eternal in human terms, a reminder of depths we're only beginning to fathom. Rest well in the moon's light. Rest well. The moon's influence weaves through human history in ways both obvious and subtle. Consider the ancient monument of Stonehenge, that mysterious ring of massive stones standing on England's Salisbury Plain. While its purpose remains debated, astronomical alignments are undeniable. The stones mark not only solar events like the summer and winter solstices but also lunar events. The monument's axis points toward the northernmost moonrise, an event that occurs only once every 18.6 years during the lunar standstill, when the moon's orbital inclination reaches its maximum. Ancient builders understood lunar cycles with a sophistication that often surprises modern observers, encoding this knowledge in stone that has endured for over 4,000 years. The lunar standstill itself is a fascinating phenomenon, caused by the precession of the moon's orbital plane. The moon's path across the sky varies over this 18.6-year cycle, reaching its maximum northern and southern positions during major standstills and its minimum range during minor standstills. Ancient cultures around the world track this cycle. The ancestral Puebloans in Chaco Canyon, New Mexico, built structures aligned to mark these events. The knowledge required to recognize a pattern that takes nearly 2 decades to complete demonstrates the depth of ancient astronomical observation and the importance of the moon in their worldview. The moon's synchronous rotation, always showing the same face to Earth, is not unique in the solar system but represents the end state of tidal evolution. Most large moons are tidally locked to their planets. Jupiter's 4 Galilean moons, Io, Europa, Ganymede, and Callisto, all show one face to Jupiter. Saturn's largest moon, Titan, is tidally locked. Even Pluto and its moon Charon are mutually tidally locked, always facing each other in their cosmic dance. This is the natural outcome when a large body orbits close enough to another body for tidal forces to act over geological time. The moon achieved this state relatively early in its history, within the first 100 million years, when it was much closer to Earth and tidal forces were correspondingly stronger. The Maria, those dark patches visible to the naked eye that form the face of a rabbit or lady that cultures have seen in the moon, filled with lava billions of years ago in a specific sequence that scientists have painstakingly reconstructed. The oldest Maria formed about 3.9 billion years ago, shortly after the late heavy bombardment, when the largest impacts created basins deep enough to crack through the lunar crust. The youngest Maria are about 3.1 billion years old. After this period, lunar volcanism essentially ceased as the moon's interior cooled beyond the point where magma could form. This means the moon's visible face has remained essentially unchanged for over 3 billion years, a surface frozen in time, displaying the scars of its violent youth. The chemical composition of mere basalts reveals that they came from the lunar mantle, melted and risen through the crust. These rocks are similar to terrestrial basalts but with key differences. They contain no water, having formed in conditions too violent and hot for water to remain. They're enriched in iron, making them denser and darker than the highland rocks. They contain unusual concentrations of titanium, with some Maria showing titanium oxide levels much higher than any terrestrial basalts. These chemical signatures help scientists understand the conditions in the lunar interior billions of years ago and map out how the moon differentiated into distinct layers as it cooled. The highlands, in contrast, are composed primarily of anorthosite, a rock made almost entirely of the mineral plagioclase feldspar. This rock type is rare on Earth but dominant on the lunar highlands. It formed when the moon's surface was covered by a global magma ocean early in its history. As this ocean cooled, different minerals crystallized at different temperatures. Plagioclase, being less dense than the magma, floated to the surface, eventually forming a thick crust. This process, called fractional crystallization, took place over tens of millions of years as the magma ocean gradually solidified from the bottom up. The concept of a magma ocean transforming into a solid world connects to a profound truth about the moon. It is a body in equilibrium now, but its surface tells the story of violent disequilibrium. Every crater, every mountain range, every dark mirror represents a moment when energy entered the system, from impacts, from internal heat, from gravitational interactions. The moon absorbed these energies and gradually settled into its current state of cold geological death. It's a monument to entropy, to the universe's tendency toward equilibrium, yet it bears the scars of every departure from that equilibrium written across its face. Humans have long projected meanings onto these lunar features. The ancient Greeks saw the face of a maiden. Some Chinese legends speak of a rabbit pounding medicine in a mortar. Indigenous Hawaiian culture saw a woman beating kappa cloth. The Maori of New Zealand saw a woman named Rona who was caught by the moon while fetching water. These diverse interpretations reveal a fundamental aspect of human cognition. Our pattern recognition abilities, so useful for survival, also lead us to see meaningful shapes in random arrangements. The moon provides a perfect Rorschach test, its surface detailed enough to suggest forms but ambiguous enough to allow interpretation. This pareidolia, the tendency to perceive meaningful patterns in random stimuli, is deeply embedded in human neural architecture. The fusiform face area in the brain's temporal lobe is specialized for facial recognition and activates even when viewing schematic faces or face-like patterns. This is why we see faces in clouds, in the patterns of wood grain, and in the moon. It's not a flaw but a feature of cognition, reflecting the critical importance of face recognition in social primates. Our ancestors who were quick to recognize faces, even potential faces, in their environment had survival advantages. The moon became an incidental beneficiary of this neural machinery. The moon's lack of atmosphere means that the boundary between light and shadow is razor sharp. On Earth, our atmosphere scatters light, creating twilight zones where illumination gradually fades. On the moon, you can stand with 1 foot in blazing sunlight and 1 in utter darkness, experiencing a temperature difference of hundreds of degrees across the width of your body. Astronauts reported that shadows on the moon were profoundly dark, much darker than shadows on Earth, because there's no atmospheric scattering to fill them with diffuse light. Only Earthshine, sunlight reflected from Earth back to the moon, provides any illumination in lunar shadows. Earthshine is itself a beautiful phenomenon visible from Earth. When the moon is a thin crescent shortly after new moon, you can often see the dark part of the moon faintly illuminated by reflected light from Earth. This was called the old moon and the new moon's arms in folk tradition. Leonardo da Vinci correctly explained this phenomenon 500 years ago, reasoning that Earth must shine on the moon just as the moon shines on Earth. His explanation was one of the early examples of reasoning by analogy in astronomy, treating Earth as a celestial body like any other rather than as a unique, privileged center of the cosmos. The brightness of Earthshine varies with Earth's cloud cover and surface reflectivity. When the moon is a thin crescent, it's positioned so that Earth, as seen from the moon, is nearly full. A full Earth as seen from the moon is much brighter than a full moon as seen from Earth, about 50 times brighter, because Earth is both larger and more reflective. Earth's oceans, clouds, and ice sheets give it an average albedo of about 30%, compared to the moon's 12%. This makes Earth a brilliant blue-white beacon in the lunar sky, far brighter than the moon appears in our sky. For future lunar colonists, Earth will dominate the sky in a way the moon never dominates ours. From the moon's near side, Earth will hang motionless in the sky due to tidal locking, neither rising nor setting but rotating through its phases over the course of a month. It will be a dynamic, colorful presence, showing weather patterns, land masses, and oceans, compared to the moon's static gray appearance from Earth. During the lunar day, Earth will be visible in the daylight sky. During the lunar night, it will be a spectacular lantern, providing enough light to see clearly even during New Earth when Earth is fully illuminated from the moon's perspective. The psychological impact of this perpetual Earth presence on lunar inhabitants is fascinating to consider. Will they feel less isolated, constantly seeing their home world? Or will the sight of Earth, so close yet utterly unreachable without spacecraft, create a profound homesickness? Science fiction has explored these questions, but the actual psychological reality will only be known when humans live on the moon for extended periods. The first generation born on the moon will have no memory of Earth's gravity, no experience of wind or rain, no sense of Earth as home in the way their parents do. What will they think when they look up at the blue world in their sky? The moon's geological stability makes it an ideal archive for preserving human knowledge and achievements. Some have proposed creating a lunar library, storing humanity's accumulated knowledge in durable form on the moon, as insurance against catastrophe on Earth. The moon's lack of atmosphere, geological activity, and life means that properly protected information could survive for millions or even billions of years. In 2019, the Arch Mission Foundation claimed to have placed a lunar library containing 30 million pages of information on the moon aboard an Israeli spacecraft, though the spacecraft crashed and the library's fate is uncertain. The concept remains appealing, using the moon as a time capsule for humanity's story. The moon has already become a cultural heritage site, though there's currently no legal framework to protect it. The Apollo landing sites contain artifacts of enormous historical significance, spacecraft components, scientific instruments, flags, and footprints. These sites tell the story of humanity's first steps on another world. As lunar activity increases, with multiple nations and private companies planning missions, there's growing concern about preserving these sites. They exist in a legal gray area, as the Outer Space Treaty of 1967 prohibits national appropriation of celestial bodies but doesn't specifically address historical preservation. The treaty itself represents a remarkable moment of international cooperation, achieved during the Cold War. It establishes that space, including the moon, is the province of all mankind and cannot be claimed by any nation. Nuclear weapons and other weapons of mass destruction are banned from orbit and from celestial bodies. Nations remain responsible for their space activities, including those conducted by private companies. The treaty has been signed by over 110 countries and is held for over 50 years, though it was written before anyone imagined commercial lunar mining or space tourism. As these activities become reality, the treaty may need updating to address new questions about property rights and resource extraction. The moon contains potentially valuable resources beyond water ice. Rare earth elements, important for electronics and green technology, are present in lunar regolith. Platinum group metals, used in catalysis and other applications, may be accessible in asteroid impact sites. The moon's low gravity makes it potentially economical to launch these resources back to Earth or to orbital manufacturing facilities, despite the high initial investment required. Some economists have argued that lunar resources could become economically viable once the infrastructure for access is established, though others remain skeptical about the business case. The concept of lunar solar power has been proposed as another potential resource. Solar panels on the moon would have advantages over Earth-based solar power: no atmospheric attenuation of sunlight, no weather, and near-continuous illumination in polar regions where the sun barely dips below the horizon. Power could be beamed to Earth via microwave or laser, though the engineering challenges are substantial. Lunar solar power represents a potential solution to Earth's energy needs that also justifies the infrastructure investment required for lunar industrialization. Beyond economics, the moon offers scientific value that's difficult to quantify. A radio telescope on the far side would be shielded from Earth's radio noise, allowing observations impossible from Earth or Earth orbit. The universe emits light across the electromagnetic spectrum, from radio waves to gamma rays, but Earth's atmosphere and ionosphere block many of these wavelengths or fill them with interference. The moon's far side offers a pristine radio environment for observing the universe, particularly at low frequencies that never reach Earth's surface. These observations could reveal the cosmic dark ages, the period before the first stars formed, when the universe was filled with neutral hydrogen emitting faint radio signals. Gravitational wave observatories on the moon have also been proposed. Gravitational waves, ripples in space-time caused by massive accelerating objects like colliding black holes, were first detected in 2015 by LIGO, opening an entirely new way to observe the universe. Lunar-based detectors could observe gravitational waves at different frequencies than Earth-based detectors, complementing ground-based observations. The moon's geological stability would eliminate seismic noise, one of the major challenges for Earth-based gravitational wave detection. The moon also serves as a natural laboratory for planetary science. Understanding the moon helps us understand Earth's history, particularly the violent early period when impacts were common. The moon preserves a record of this era that Earth has largely erased through plate tectonics, erosion, and life's activity. By studying the moon, we learn about the conditions that existed when life was emerging on Earth. The moon is a witness to Earth's story, and learning to read the testimony recorded in its rocks gives us insight into our own planet's past. The search for life beyond Earth may also have lunar connections. Some scientists have proposed that Earth rocks ejected by asteroid impacts could have reached not just the moon but other planets and moons in the solar system. If early Earth harbored life, these rocks might have carried microbial life to other worlds, a process called panspermia. The moon, being nearby, would have received many such rocks. While the harsh conditions would likely sterilize the surface, rocks that buried themselves deeply might have preserved evidence of early Earth life. Searching for ancient Earth life on the moon is an intriguing possibility, especially life from the earliest periods that left little trace on Earth itself. The moon's influence on life's evolution beyond providing stability and tides is difficult to pin down, but some researchers have speculated about more direct effects. The theory of tidal evolution suggests that the moon's strong tides on the early Earth might have created tidal pools where complex chemistry could occur, potentially contributing to the origin of life. Tidal rhythms may have influenced the evolution of circadian and circulunar rhythms in early organisms. The moon's light may have driven the evolution of eyes and light-sensing organs, as there were advantages to being active during moonlit nights. These ideas remain speculative but point to the moon as potentially playing a role in shaping the trajectory of life on Earth. Lunar eclipses have historically served as natural experiments in atmospheric science. During a total lunar eclipse, light passing through Earth's atmosphere is refracted onto the moon, and the color of the eclipsed moon depends on Earth's atmospheric conditions. Volcanic eruptions that inject large amounts of aerosols into Earth's atmosphere can make lunar eclipses darker and redder. By comparing the color of different lunar eclipses, scientists can learn about historical volcanic activity and atmospheric composition. Ancient observers who recorded eclipse appearances were unknowingly documenting Earth's atmospheric history. The color of the moon during an eclipse is described by the Danjon scale, ranging from 0, very dark, moon almost invisible, to 4, bright copper red or orange. This scale, developed by French astronomer André Danjon in the 1920s, provides a standardized way to describe eclipse appearances. The variation in eclipse colors reminds us that even when we're looking at the moon, we're also seeing information about Earth, refracted through its atmosphere, painted across the lunar surface. The moon's synchronous rotation means it experiences an unusual day-night cycle. From the moon's equator, the sun rises in the east, moves slowly across the sky over the course of about 2 Earth weeks, then sets in the west, followed by 2 weeks of darkness. This means any given location on the moon experiences about 354 hours of continuous sunlight followed by 354 hours of continuous darkness. For solar-powered equipment, this creates challenges, as power systems must store energy for the long lunar night or use alternative power sources. The poles offer a partial solution. Some crater rims near the poles experience near-continuous sunlight, with the sun barely circling the horizon. These peaks of eternal light are prime candidates for lunar bases. Conversely, some polar craters are permanently shadowed, never receiving direct sunlight. These craters, called cold traps, maintain temperatures cold enough to preserve ice for billions of years. The presence of water ice in these craters, confirmed by multiple spacecraft missions, is one of the most important lunar discoveries of recent decades. This ice represents not just a resource for future explorers but also a scientific treasure. Some of it may date back billions of years, potentially containing pristine samples of ancient comets and asteroids that delivered water to the inner solar system. The process of confirming water ice on the moon involved multiple lines of evidence. Neutron spectrometry detected hydrogen, which could indicate water. Infrared spectroscopy detected the specific absorption features of water ice. Radar observations showed reflection characteristics consistent with ice. The concentration of ice varies by location, with some areas containing relatively pure ice while others have ice mixed with regolith. Extracting this ice will require technologies that can either excavate and process ice-bearing regolith or heat the regolith to release water vapor. The moon experiences meteorite impacts at a much higher rate than Earth because it lacks an atmosphere to burn up incoming objects. Small meteorites that would become meteors in Earth's atmosphere strike the lunar surface intact. The impact rate for objects larger than a centimeter is roughly estimated at about 33 kilograms of material striking each square kilometer of the moon per year. These constant impacts gradually churn the lunar regolith, a process called gardening, mixing it over millions of years. The top few inches of regolith have been completely turned over multiple times through this process. Occasionally, these impacts are visible from Earth as bright flashes when particularly large meteorites strike. Amateur astronomers have recorded hundreds of these impact flashes during moon watches, particularly during meteor showers when the Earth-Moon system passes through streams of cometary debris. These flashes, lasting only a fraction of a second, release energy equivalent to hundreds of kilograms of TNT exploding. They create new craters that, though small, add to the moon's ever-accumulating collection of impact scars. The youngest craters are of particular interest to scientists because they provide information about the current impact rate, helping calibrate crater dating methods. The absolute ages of surfaces can be determined by radioactive dating of samples, but for most of the solar system, we can only use relative dating based on crater counts. More craters means an older surface. Understanding the current impact rate helps convert crater counts into actual ages. The moon serves as a calibration target for this technique, which is then applied throughout the solar system. Some lunar craters show unusual features that hint at the complex physics of hypervelocity impacts. Impact melt, rock that was liquefied by the energy of the impact and then solidified, often pools on crater floors or appears as sheets and dikes around the crater. Some craters show evidence of central peak formation happening in slow motion, as minerals found in the peaks show shock metamorphism, indicating they came from deep below the surface, but also show textures suggesting they were heated and deformed as they rebounded. The violence of large impacts creates conditions that don't exist anywhere else naturally on the moon or Earth. Pressures and temperatures that transform minerals and melt rock in microseconds. The largest impact basin on the moon, the South Polacan Basin on the far side, is one of the largest known impact structures in the solar system. It measures roughly 1,600 miles across and up to 8 miles deep, though its depth has been partially filled by later impacts and lava flows. The impactor that created it would have been an asteroid perhaps 125 miles in diameter, striking at tens of kilometers per second. The impact would have been visible from Earth as a brief new star, if anything on Earth at the time had eyes to see. It may have excavated material from the moon's mantle, offering a window into lunar interior composition. Future missions plan to explore this basin, seeking those deep mantle materials. Understanding the moon's interior helps constrain models of its formation and evolution. The giant impact that created the moon should have mixed Earth and Thea's materials, but how thoroughly they mixed and how the moon differentiated afterward remains uncertain. Samples from the South Polacan Basin could answer questions about the moon's composition and, by extension, about the composition of the early Earth and the impact process that created the Earth-Moon system. The moon's cultural significance extends into modern times through holidays and festivals. The Mid-Autumn Festival, celebrated in China, Vietnam, and other East Asian countries, honors the harvest moon with mooncakes, lanterns, and family gatherings. The Islamic calendar, being purely lunar, means holidays like Ramadan and Eid shift through the solar year, occurring 11 days earlier each year. This connection to lunar phases keeps practitioners attuned to the moon's cycle throughout the year in a way that solar calendars don't require. the moon remains woven into religious and cultural practice for billions of people worldwide. The aesthetic appreciation of the moon spans cultures but shows interesting variations. In Western art, moonlight is often depicted as silvery or blue-white, while in some Eastern traditions, particularly Japanese art, moonlight may be rendered with warmer tones. The moon viewing tradition in Japan, called tsukimi, treats the autumn full moon as an aesthetic event worthy of poetry, specific foods, and contemplative observation. This formalization of moon watching into a cultural practice reveals how deeply the moon can be integrated into a society's seasonal rhythms and aesthetic values. Moonlight has practical as well as aesthetic significance in photography and cinematography. Before artificial lighting, moonlight scenes in film were often actually shot during the day using filters to darken the sky and desaturate colors, a technique called day for night. Real moonlight, while bright enough to see by, is too dim for older film stocks to register detail. Digital cameras have changed this, making true moonlit cinematography possible. The unique quality of moonlight, softer and more diffuse than direct sunlight, creates a particular mood that filmmakers use to evoke mystery, romance, or danger. The moon's influence on language extends to technical terminology. The word month derives from moon, as mentioned earlier, but many other words carry lunar etymology. Monday means moon's day in numerous Germanic languages. Menstruation shares a root with month and moon, all deriving from concepts of measurement and cycles. Lunar, selenite, lunacy, honeymoon. The moon has left linguistic fingerprints throughout the vocabulary of time, change, and illumination. The philosophical implications of the moon's existence extend to questions about cosmic purpose and anthropic reasoning. The moon's size relative to Earth, its distance allowing perfect solar eclipses, its role in stabilizing Earth's climate, these features seem almost designed for the emergence of intelligent life. Some philosophers and scientists have noted these apparent coincidences, with some seeing them as evidence for design and others seeing them as selection effects. We observe these properties because we exist in a universe where they occur. In universes or solar systems without such fortunate arrangements, no observers would arise to notice their absence. This touches on the anthropic principle in cosmology, the observation that the universe's physical constants appear fine-tuned for the existence of complex chemistry and life. The moon's properties could be seen as a planetary scale version of this apparent fine-tuning. However, most scientists interpret these observations through selection bias rather than design. We exist in one of many possible planetary systems in a vast universe, and naturally we find ourselves in one compatible with our existence. The moon's benefits to Earth may be fortunate accidents rather than purposeful design, but they're no less real for being accidental. As you lie here, consciousness gradually releasing its hold on waking thoughts, you participate in your own circadian cycle, the daily rhythm of alertness and rest that governs all complex life on Earth. This rhythm evolved in a world with days and nights, with sunlight and moonlight, with predictable cycles that organisms could anticipate and prepare for. Your body knows, at a cellular level, that night is for rest, for repair, for the unconscious processing of the day's experiences. Sleep is not mere passivity but an active state where the brain consolidates memories, clears metabolic waste, and prepares for the next day's challenges. The moon, hanging in the night sky, has witnessed every human sleep throughout history. It was there when your ancestors slept in caves, when they built the first cities, when they crossed oceans seeking new lands. It was there through every dream humanity has ever dreamed, every thought in the night, every moment of rest. It will be there for all the sleeps to come, for as long as humanity endures. In this way, the moon is a thread connecting past, present, and future, a constant in a changing world, a reminder that some things endure beyond individual lives. Let yourself sink deeper now, releasing the day's concerns, trusting that the world will continue without your vigilance. The moon will continue its orbit, Earth will continue its rotation, the cosmos will unfold according to the laws that have governed it since the beginning. You need not maintain these things through your attention, they proceed whether you wake or sleep. This is one of the gifts of understanding nature through science, the knowledge that the universe is reliable, that cause follows effect, that patterns persist. You can rest in this reliability. The moon teaches patience. It reminds us that some changes are too slow to perceive in a human lifetime but are nonetheless real and profound. It teaches us that cycles exist at many scales, from the rapid beating of hearts to the slow drift of continents, from the fleeting spark of thought to the billions of years of stellar evolution. The moon exists at a middle scale, its monthly cycle fast enough for humans to witness yet slow enough to instill patience. As sleep approaches, your brain shifts through different states, moving from waking consciousness through drowsiness into light sleep and eventually into deep sleep where consciousness fades almost entirely. This nightly journey into unconsciousness is one of life's great mysteries. Where does consciousness go during deep sleep? What is the experience, if any, of a sleeping mind? These questions remain at the frontier of neuroscience and philosophy. Sleep and death have been compared since ancient times, sleep being called little death in various traditions, a temporary cessation of consciousness that previews the final cessation. But sleep is also renewal. You will wake tomorrow, consciousness returning like the new moon emerging from darkness. The same processes that fade awareness into sleep will reverse, bringing you back to the world of thought, perception, and action. The cycle continues, as reliable as the moon's phases, as necessary as breathing. In this sense, sleep is optimistic, an act of faith that tomorrow will come, that rest now serves future wakefulness. The moon, in all its phases, reminds us that darkness is temporary, that what wanes will wax again, that endings contain beginnings. The new moon, invisible in the sky, is not the moon's death but its preparation for rebirth as a thin crescent, growing night by night toward fullness. This pattern, repeated throughout your life, throughout human history, throughout the billions of years of the moon's existence, speaks to something fundamental about time, change, and persistence. Rest now in this knowledge. Rest knowing you're part of ancient patterns, contemporary with the moon and stars, breathing the same atoms that have cycled through countless lives and will cycle through countless more. Rest knowing that mysteries remain, that wonder persists, that tomorrow the moon will still be there, changed yet constant, new yet eternal. Rest in moonlight, in darkness, in the gentle dissolution of waking consciousness into sleep's embrace. The moon keeps watch over the sleeping world, as it always has, as it always will. Let its light guide you gently into dreams, into rest, into the renewal that sleep brings. The story continues tomorrow, but for now, the story is rest, is peace, is the slow breathing of sleep, is the quiet joy of consciousness releasing its grip and allowing the body to simply be. Sleep well under the moon's ancient light. Sleep well.